Now that we are familiar with assertions, preconditions and postconditions, let's get introduced to another term, which is invariance. So an invariant, you may have studied about invariance when you talk about even the introductory course in computer science, because invariants are typically the way to reason about correctness of a program, and that's typically what you need to do when you are using formal methods to prove the safety and security of a program as well. So we're going to define what an invariant is more formally. An invariant at a given program point is an assertion that holds during execution whenever control reaches that point. So whenever, at a particular PC program location in the program, whenever during execution the control reaches that point, this fact is always true. And if such a fact exists, if such an assertion exists, then that's called an invariant. Okay, so let's look at an example. This is the example of the Euclidean integer division program. So the precondition of this program is that both x and y are greater than 0, and x can additionally be equal to 0. So x is greater than or equal to 0 and y is strictly greater than 0. So, and then there is the program. If we look at the program, it is, it basically initializes the quotient q to 0, the remainder r to x, which is the dividend. And then while r is greater than or equal to y, with y is a divisor, you do r equals r minus y, you decrease r by y, and you do q equals q plus 1, you increase the quotient by 1. And this program, when it ends, it's supposed to give you the result of division, the quotient in q and the remainder in r. So first of all, this x greater than or equal to 0 and y greater than 0 is a precondition. So even a precondition is an invariant which is enforced by the external environment that calls this program. And this invariant holds at the program location, which is the entry of this program. So right here, this assertion x greater than or equal to 0 and y greater than 0 can be assumed to hold. And it's an assertion that holds whenever whenever execution reaches this point. And so the precondition itself is an invariant at the beginning of the program. But there are more invariants that we can identify at other points in the program, and here are some examples. So for example, just after executing q equals 0, the invariant is whatever was existing before, which is x is greater than or equal to 0 and y is greater than 0, and we can further claim that q is equal to 0, because we're sure that at this point q would always be equal to 0 because we just assigned q to 0. Similarly, after the second statement is executed, which is r assigned to x, we know that everything that was holding earlier, which is x is greater than or equal to 0, y is greater than 0, q equals 0, and r equals x. So there are four different predicates here that are conjuncted using the conjunction operator, the AND operator, which is basically the invariant at this particular point of this program. Once again, this is an assertion that will always hold whenever the program control reaches this point. And of course, we are assuming that the precondition already holds, and precondition is being imposed by the environment, but all the other things are kind of following from both the precondition and the properties of the program, such as the assignment operators. We haven't yet discussed how to identify these invariants or etc. We're going to talk about that later on, but at least we should know what are the invariants or what are the possible invariants. Now the next invariant example is actually interesting because this time I have a loop, and so I can come to this point which is just after checking whether r is greater than or equal to y or not from two paths. One is coming directly from the entry path, and the other is through the loop path. And so when I come here, I can no longer say that q equals 0, or because q is getting incremented on the loop path. I can also no longer say that r equals x, because once again, on this path, r is getting changed. R is becoming r minus y. What are some invariants that I'm sure of? So I claim, and I'm going to show why, that one of the invariants is that r is greater than or equal to y. Now this is easy to see because if I am at this location, I can only reach this location after I have basically checked whether r is greater than or equal to y or not. And if r was not greater than or equal to y, I wouldn't have even reached here. I would have actually exited the loop. Similarly, let's look at the other invariant, which is r is greater than or equal to 0. So I know that r is greater than or equal to 0 because I know that if I'm coming on this path, then r was equal to x, and we know that x was greater than or equal to 0. And so from that I know that if I'm coming here from the entry, then R is greater than equal to 0. Moreover, because I know that if I look at the loop path, then I get R equals R minus Y, but I already know that R is greater than equal to Y. And so if I do R is R is equals R minus Y, then that basically means because R was greater than equal to Y, R minus Y will be greater than equal to 0, and so that also gives you R greater than equal to 0. In fact, this actually directly follows from the fact that Y is greater than 0 and Y hasn't changed. So because R is greater than equal to Y, R is greater than equal to 0 as well, because by transitivity of the greater than relation. Similarly, I can prove that Q is greater than equal to 0. So, I'm sure that whenever program control reaches this point, Q will be greater than equal to 0. How do I know that? Well, you can see that in the first time I come here, Q is equal to 0. And then every other time I come here, I have probably incremented Q by 1. And so I cannot ever have a negative value of Q, and that's another invariant that I can prove at this particular program location, or it's another invariant that actually holds for this particular program location. And finally, I can also have an invariant for the program exit, and this will be our post condition. And once again, I could basically say Q is greater than equal to 0, and that's just going to follow from the fact that Q was initialized to 0 and it can only get incremented. So Q is greater than equal to 0. R is greater than equal to 0. Once again, it's the same logic because R was greater than equal to Y. And I could have at most done R equals R minus Y. So that basically, because R was greater than equal to Y, R minus Y would have been greater than equal to 0. And then R would have become less than Y, and I would have come here. So R is greater than equal to 0. And the third one is R is less than Y. And why do I know that? The fact that I've exited the loop basically is evidence that R must be less than Y, because if R was not less than Y, I wouldn't have exited the loop, because the loop condition is basically that R is greater than equal to Y. So these are some invariants, some examples of invariants in this particular program. Okay, once again, invariants are just assertions that hold. And how do I prove that these invariants actually hold? These invariants actually hold at the respective program points. So if I look at these three things here, I need to show that it holds for the base case, which means if I assume that x is greater than equal to 0 and y is greater than 0, and I execute these assignment statements, q gets 0 and r gets x, and also I execute this branch statement which says if r is greater than equal to y, and I actually reach this point, which means the branch was actually evaluated to true, the branch condition was evaluated to true, then this is the condition that I get on the loop head. So I need to prove, so one thing, the first part of the proof is going to be, the first part of the proof that the invariant actually holds at this point is going to be that it holds for the base case, which is the entry path. And the second part of the proof is going to be the inductive hypothesis and the inductive step, which is assuming it holds at any arbitrary kth iteration, it also holds for k plus 1th iteration, where k is a natural number. So if it holds for the first iteration, then it also holds for the second iteration. If it holds for the second iteration, it also holds for the third iteration, and so on. And so this is also easy to see. I actually discussed this before actually talking about the proof. Because if r is greater than equal to y, and I kind of take this path, then I've already kind of executed and I've reached this point, then that basically means that r would still be greater than equal to y. Similarly, I can prove that q will be greater than equal to 0 because I'm only incrementing q, and I can also show that r is greater than equal to 0 because r is greater than equal to y, and r minus y thus would be greater than equal to 0. Alright. And so this kind of method of identifying or kind of proving that certain invariants hold is based on the induction on the number of program steps. This is step 1, or you can basically, depending on what granularity you are counting steps. If I just count the whole thing as one step, then this is one step, and then every iteration can be counted as another step. And so if I just do induction on the number of steps that the program has executed, I can show that this invariant holds. And for this reason, these invariants are also called inductive invariants, because because it's an inductive argument that you use to show that these invariants actually hold at their respective program points. Now, those were some invariants, and these are just some examples of invariants. But there are some invariants that are more useful than others. For example, in this program, it is the Euclidean integer division example, and so one of the properties that I want to prove is that when this program exits, then I get the right answer in Q and R, which means Q is basically the quotient and R is the remainder, which basically means that X should be equal to QY plus R. Moreover, R should be less than the divisor, which is R should be less than Y, and R should be greater than equal to 0. And so this is the post condition that I want to prove. This is the property of the program that I want to prove. This is the partial correctness condition that I want to prove. And if I want to express this partial correctness condition, I would say the precondition of the whole triple would be X is greater than equal to 0, comma Y is greater than 0. The program C would be this whole program that involves a loop. And the post condition would be these three statements, which is R is between 0 and Y, including 0. Q is greater than equal to 0 and X equals QY plus R. And we want to prove this, and to prove this we basically need invariants at some intermediate points in the program. In this particular case, I especially need an invariant at the loop, somewhere inside the loop body, maybe at the head of the loop, where we basically want to say, okay, can I say something here which basically allows me to show that this invariant holds at the program exit. And I want to point out that the current set of invariants that we have are not sufficient to prove this property. Although these invariants are actually, they hold, we've already shown that these invariants are correct. They are not good enough, they are not sufficient to actually prove this property that X equals QY plus R at exit. Because, how do I show that if I am at the loop head and I exit the loop, then I know that X equals QY plus R. I don't have enough information at the loop head to be able to say that this is going to hold. On the other hand, if I never took the loop, then this is obvious, because if it was Q equals 0, R equals X, and then R is greater than equal to Y actually evaluated to false, that basically would obviously mean that R is less than Y, and because Q is 0, so 0 into Y plus R is X, so X equals 0 plus X, and that's true. So if I don't take the loop, it's clear that this holds at the program exit. But if I take the loop, then I don't have enough information in the invariants at the loop head to be able to prove that this invariant holds at program exit. So here is the solution to this problem, and the solution is that we kind of strengthen the invariant at the loop head. I'm using the word strengthen, basically saying make it more precise, which basically means have stricter covers or have stricter abstractions. Recall that when we said that an assertion is an abstraction, we're basically saying that it's an envelope over all the behaviors. The loose, if an envelope is loose, we say it is a weak abstraction or it's a weak invariant. If the envelope is tight, then we say it's a stronger abstraction or a stronger invariant. And in this case, we can strengthen the invariant by tightening the abstraction. So by adding one more predicate as a conjunctive clause and say, in addition to these three, another fact holds at the loop head, which is X equals QY plus R. And once again, you would see that it is possible to prove this using the same inductive argument. When I come from entry, then Q would be 0 and R would be X, so this holds. And if it holds at the kth iteration, and I make one iteration here, then I just decrement R by Y and increment Q by 1. And you will see that if it holds in the kth iteration, it also holds in the K plus 1th iteration. Moreover, if it holds for any kth iteration here and I don't come back to the same location, and instead if I exit the loop, once again I can show that because X was equal to QY plus R and I just executed the body only once, when I come out, I know that R is less than Y, and I would know that X equals QY plus R, because once again by the same argument, R has been decremented by Y and Q has been incremented by Y, Q incremented by 1, and so that kind of makes this program assertion still hold. We're going to see this more mathematically, these proof obligations, also called verification conditions, more formally in our next module, but I just want to kind of motivate the fact that identifying the correct invariant at the loop head is of prime importance. In other words, identifying the correct abstraction for my program at different program points is important, because if I identify an abstraction that's too loose or an invariant that is too weak, then that does not allow me to prove my desired post condition, in this case X equals QY plus R. But the moment I strengthen it appropriately, then I'm able to identify the corresponding proof for that required post condition. So here is the proof. I mean, if I come from the entry, then this holds. And if I take one iteration, if I assume that it holds in the beginning of the kth iteration, then I can show that it also holds at the beginning of the k plus 1th iteration.